Hi, welcome to the Noise Path. Now, a lot of people on Patreon always ask me to make even quick videos of the stuff that's happening around the lab, and I promised to do more of these microwave components. We went ahead and picked up a couple of these fairly high-end amplifiers, and thanks again to all the Patreon supporters. If you want to support the channel, please do check out the page. So I have three amplifiers here. The one on the left is from 10 megahertz to 26.5 gigahertz. This is a low noise amplifier, and this one is from 26 to 40 gigahertz. These are essentially continuation of each other in a fairly broadband system. Now there's something wrong with all these amplifiers, so we're going to have to test them, and these are not often repairable because they're based on some mimic that essentially is the entire thing. The rest of it is just biasing. So we'll take a look, and if they're repairable, great. If not, we can still learn something about the architecture. Now this SHF unit, this is more of a power amplifier. Works from 30 kilohertz to 25 gigahertz, and you can see it puts out almost 26 dBm or so as saturated output power. It runs from about 11 volts, and it does have a broken pin, and it is missing one screw. So I wonder if the simple problem of this is just that the fact that this pin is broken. That would be fantastic because it would be a really easy fix, but we will get to see what's inside it anyway. This pin, you can see a similar one over here. These often break because somebody solders a cable to it that's very thick, for example, and as the cable moves around, this pin is not flexible and it will eventually snap off, and once it snaps off you can't turn it on anymore. So we'll have to take a look and see if it's possible. Let's start from the little ones. First we're going to measure their S parameters to see if they do anything at all, and then hopefully we'll fix them. And here is our measurement setup. We're going to use the Keysight Field Fox. This is a 50 gigahertz unit, of course has a 2-port network analyzer, so we can measure our amplifiers in S parameter mode and see what they do. These are paired with some John Korsha cables. These are fantastic cables as well. I'll do a separate video about that, but the review of the Field Fox is already on my channel. Definitely check it out and you can see all of its capabilities. So right now I have mounted the 26 to 40 gigahertz amplifier first. Let's take a look at its S parameters. Okay, so here we go. Let's turn the power back on. What do we have? There it is. Well, it is doing something. So here's the zero line, as you can see, and here's the gain of the amplifier. It doesn't really look very promising, unfortunately. Looks like something's happened to this particular amplifier. Let's put a marker over here. So here's the 26 gig is right here, so it does go below 26, and 40 gigahertz is, oh, it's already dropping. 40 gigahertz is here. The gain is minus 25 dB at 40 gigahertz. Yep, this amplifier has definitely been damaged. Now the fact that it does have a reasonably flat gain everywhere else might be just an output. Something might have happened to the output network, so when we open it we can take a look at it. So this one, something's definitely wrong with it. Okay, let's repeat this experiment for now the 10 megahertz to 26 gigahertz amplifier. Let's turn it on. Here we go. Looks a little better. Definitely has some gain. Goes as high as 20 dB. Let's see where it is at 26 gigahertz. Here's 26 gigahertz, 17 dB of gain. Not bad. Somewhat respectable. We go down over here, but there you go. At 1 gigahertz, it's dropping. At 4 gigahertz, already at 6 dB. Yeah, it doesn't look very good neither, but it is at least somewhat functional. I could use this in the lab for some experiments. If it's not fixable, it's not great, but I guess it's doing something better than nothing. And it's burning 150 milliamps from 15 volts. Okay, all right. Well, let's take a look at these. Okay, one screw left here. So I'm curious how they put this together. It's a reasonably high frequency amplifier. Ah, this is anticlimactic. All right. So it seems like they have attempted to hermetically seal it. Okay, so this is going to be unfortunately a destructive opening of this, but since we know this is dead, for sure, I'm okay with it. We get to see how it's built. There's two other screws here, so let me remove those as well. I think this module should come out. All right, here it is. So it has two windows, one here and one here. That's where the biasing is done. This is where the amplifier is. Obviously at this magnification you can't see anything. We're going to have to put this under a better microscope, but we should be able to take a good look at it. All right, so here's what's on the inside. So this looks like we have multiple stages here. On the left is our input connector all the way here. And then we have 1, 2, 3, and 4 stages. And then to the output. Now those big white ceramic pieces that you see, those are just interconnects and matching network. The little black spots, that's the actual transistors. Now from this distance, they look like gas PHEMs to me. So they're using 4 of them, and that's how they get the gain required, although this one obviously doesn't work. But yeah, nothing really unusual there. We have to take a closer look at those, but if I rotate this, you will see the bias network. Let me focus on this. There it is. So we do seem like we have a voltage regulator IC in the middle. So the power comes in through this pin, goes over there. There's some wire bonds. Those big golden pieces that you see are actually vertically mounted capacitors. So they are wire bonding directly on those, and then there's some capacitors, smaller ones, in parallel to it. And then they bring those wire bonds into the voltage regulator. From the output of that, we go into another ceramic piece with thin film resistors, which they can trim out. You can see there's actually a jumper across one of them, and that's how they get multiple different resistances. And it seems like they generate two biases, probably the drain and the gate bias, essentially, to be able to create those amplifiers from those gas PHEMT transistors. And those biasing go through this little hole and go all the way through, and without touching anything, of course, because they would short out. And then they go into a series of capacitors which are mounted everywhere. That's how they distribute the bias. You can clearly see it. These long bond wires running everywhere, and then go into the ceramic pieces. Very nice. There's some decoupling capacitors on the ceramic pieces. You can see the outputs going directly onto them. That's how they decouple the stages from each other and prevent their biasing from interfering with each other. But at this distance, it's very difficult to know what's gone wrong, because those PHEMT gas devices, if that's what they are, they're not visible at this range. We need a much fancier microscope to see it. Well, we do have that, so we should be able to take even a closer look. Okay, here's our fancier microscope. We should be able to take a really close look at those devices now. So here's that ceramic piece that you can see now. There's wire bonds right on it. And here is our device. Let's focus on that. Look at that. Looks very nice. Definitely does look like a gas PHEMT to me. I could be wrong, but I think that's what it is. So we have a couple of wire bonds going into it. Looks good. Let's go on to the next stage. Just go down the line. These are at very different levels. Here's another one. Still looks pretty good. Continuing on. Oh, by the way, here's the decoupling capacitor I was talking about. There you go. Here's the top surface of it. You can see how tall it is by the relative focusing plane that I have to go through in order to see the top of it. So it's a fairly large device, actually. You just can't see it. A lot of scratches. Wow, this one has a lot of wire bonds. This is probably the master biasing one. They're probably bringing in the biasing from here and then distributing it out, so it has multiple wire bonds on it. Looks really funny. Let's keep going. And here's the last one. Oh, wait a second. Ah, look at that. Do you see it? Right in the middle, you can see the gate is peeled off. You see how that gate is not even on the device anymore? So if I focus on everything, the top gate is not even there, the vertical line. Yeah, there's something wrong there. There it is. Now I'm focusing on the top gate. Say, you can see that it's not in the same focal plane at all. Something's gone wrong with this one. That's interesting. I wonder what has happened. Maybe stress over time? Just so we can compare this, I'm going to go back to one of the other ones. Not this one, because there's so much stuff on it. But here you go. You can see how nice and flat the gate is on this one. Completely different. Well, that explains the... Unfortunately, that's not fixable, as you can imagine. But there it is. Yeah, that's what has happened. Okay, well, that tells us something. Not repairable, but very interesting nonetheless. We should look at the voltage regulator too. And here is the voltage regulator. Can you guess what voltage it is? I don't know. I wonder if somebody could have maybe put a hint on it on the layout. F77T. That could be some part number. There's a really big transistor at the output. So the reason this is not in focus here is because it's actually not flat. So the focal plane is extremely shallow on a microscope like this. So it's very hard to see everything in focus at the same time if the die is not flat and whatever they've mounted it on. So I have to keep refocusing. There's some additional transistors and some feedback network. It is, I believe, is a voltage regulator. But if you find out what it is, let me know. Looks good. We can also look at some difference interference contrast microscopy. There we go. Look at that. How beautiful is that? Super cool. You can actually see a rough 3D view. There you go. You can see differences in the height very well with this kind of microscopy technique, which I've talked about in some of the other videos. Very cool stuff you can do in optics like this. And you can even see the surface roughness of the metal and create different contrasts and different kinds of 3D effects almost because of how it works. Very cool stuff. Yeah, interesting. So here's what's inside the other unit. And this is the pin that's broken, but it comes in through and it goes into a capacitor. So if we can find the replacement pin for this, this should be no problem. Now this has two parallel biasing network, one over here, one over here. These are RF absorbers placed on top. There's a decoupling capacitor in the middle, one at the beginning and one at the end as well. And there are two mimics. Now these are fully isolated from each other by these capacitors, but they're also fully covered. So I can't see anything on the die, so there's really no point looking at it under the microscope any more than this because you can't see it, which means that if those dies are bad, of course there's nothing you can do about it. Again, we're back into the same situation. But if this pin is broken, this may have just simply been the only issue here. And you can also see all the other biasing stuff that's put there, peak decoupling capacitors and inductors and so on, typical stuff. And the biasing very, very close to the die is handled with some very thin wire bonds, which you cannot see neither. So what I'm going to do, I'm going to remove this, and I wonder if this one, the one we just opened, if this is thread compatible with this and it's the same size, because then we can just salvage this one, which is the one that's not useful anymore anyway, and use that. That would be nice. At least something can be repaired this way. Okay, so unfortunately they're not exactly the same. So I'm going to borrow one from this mini circuit amplifier, which I think has the same one. Sorry, mini circuit, I will return that when I find the replacement. This is a 500 megahertz low noise amplifier, 2.9 dB of noise figure, which isn't really no noise for 500 megahertz, but nonetheless, we'll return this later. For now, I think the other amplifier is quite a bit more valuable to repair. And here's inside of this amplifier, in case you were wondering. It's based on 2 individual transistors, and it doesn't even have a varactor in the middle for tuning. It's totally surface mount, nothing unusual, but we should be able to take the connector away from it. There we go. I think it looks pretty good. Let's give it a try. Okay, so here's a similar setup. The only difference is that there is a 6 dB 26.5 gigahertz attenuator at the output of this, because the saturated output power of this is 26 dBm and this guy can only take 25. I don't need this because I'm not putting enough power in it to saturate it, but nonetheless it's always good practice to be safe and protect the instrument, which is a lot more valuable than the attenuator. Okay, applying power, and check it out, it looks very nice. So what do we have? We have 12 dB of gain. This is supposed to be an 18 dB amplifier. There's a 6 dB attenuator, so it lines up perfectly. Let's see what the bandwidth is. So we're looking for 8 dB. That's when the gain roughly hits about 8 dB or so. If I go based on that, we have a bandwidth of about 27 gigahertz, which exceeds the specification of 25 gigahertz. So it's a very nice broadband amplifier, typically used for drivers and so on, perhaps in some optical application. That's probably where it came from. But it's good, it's repaired. And there you go. I hope you enjoyed this. As always, thanks to the Patreon supporters for making these things possible. Let me know in the comment section if you like these kind of videos, and I'm sure I can do a few more of these here and there in between the longer videos.